All right, so in this exercise, we're going to practice using our micrometers. Hopefully you watched the video where I explained different techniques for how to use these different situations, how to calibrate, how to clean, how to use it in general. So we're going to go through some practice exercises. You can find this practice exercise on the Pragmatic Metrology website. You can also find prints for this part as well as the step shaft there, which we're going to use for this exercise. You're more than welcome to substitute your own parts if you don't want to make this or 3D print it. But just make sure you grab something with reasonably similar features so that you can follow along. Grab the exercise from the website as well as the worksheet for filling out your measurements. This worksheet is very similar in design to inspection sheets that you'll find in industry, although a somewhat simplified version so that we can just practice what we're doing. But they'll look a lot like this, different formats. Some have different information, but it's a good practice for you to get used to. So go ahead and grab this while you're there. So let's just get started. Let's jump into the practice exercise with the OD micrometers. We are gonna let's read through the exercise description. So I'm gonna read it here off my sheet. Practice measurement with OD micrometers. Practice reading the Vernier scale and performing the addition correctly. Work out pressure for measurement using the ratchet, a friction thimble, and feel. I don't have a friction thimble micrometer. Oh, actually, yeah, we can use this one. So we will try to demonstrate the differences between them. You just need to practice all three because you're going to be using all three probably in your career if you're watching this. So let's go through the instructions. First thing, check your micrometers for good calibration, inspect cleanliness, practice calibration of mechanical tools, practice setting zero on digital tools, check zero with multiple blocks, check for the frames being bent. So we did this in the other video, but I will go ahead and redo calibration check, make sure everything's in good condition. So let me flip over to the other monitor. So I'm going to start off making sure it's clean. I keep these micrometers very clean, so there shouldn't be any chips or oil on them. But I'm going to wipe off the tips, the handles, and we're going to check for smooth movement. I'm going to bring it to zero very gently. As I get closer, I'll go slower. And let's see, is that reading? That looks like zero to me. I don't know what you think. I can't quite get on the screen. Remember, you can always check the secondary camera feed where it's much, much clearer than what shows up here on the monitor. I'm trying my best to get a clear picture, but it definitely looks a lot better here. So feel free to jump over to that video if you want to watch a bird's eye view, exactly what I'm seeing. So we got zero there. I don't need to, thankfully, I don't need to adjust it. If you watch the video where I adjusted a micrometer and I was chasing it back and forth. Don't need to this time. So we'll check the 500 block like we did in the other video. And I'll use my ratchet. So how's that look? That looks like it's just a fraction off, maybe a tenth off. This is kind of what we saw before. We'll look, see what line fits best. In my eye, it's the 9/10. I don't know if it's hard to show that on the camera, but for me, the 9/10 looks like it lines up best. So we're about a tenth off. That's a little concerning, but we'll go ahead and we'll check the full stroke again. Could, it just means there's a little bit of error at the half-inch mark, and there may be error in other places. And if you're concerned about that, check more of these blocks. I'm a little concerned. I'm going to check 1 inch, and we're going to see how it finishes its stroke. So again, just a hair below. Looks like the 0.9 is below again. So it's It's within my limits. You know, 1/10 can be really hard to take out a micrometer, as you saw. So we're gonna keep using it. It feels smooth. I'm not seeing any friction that shouldn't be there or any bad conditions all around. So I think we're in good shape. Our frames don't look like they're bent. I only got 1/10 difference. So it's very small. I don't have a digital tool to check with, but it's essentially the same thing. You close it, check for zero, and if you need to zero it, there's a zero button. You can reset the origin for zero. When you have a larger micrometer, you go through the same process, but you have a standard in the box that you can check with. And let's see. When the standard spins freely, oh, it snuck out. I'll do it again. When the standard spins freely, we're looking good. And from my point of view, we're looking maybe a 10th high, not even a 10th high. But it's, I think, good enough to use. If I had I could use more Joe blocks to check the range of that one as well, but we're gonna move forward with what we've got right now. We're gonna go back to number 2 on our worksheet. We've done number 1 where we check for good calibration. Let me fix the size of this real quick. All right. So number 2, part measurement. Inspect parts with micrometers. Identify and only measure the features that the tool are capable of. Repeat measurements with calipers. So double check yourself. Consider what might be easier to work with, micrometers or calipers. You know, these are 2 tools you're always going to be choosing between, or you're going to be double checking with the 2 of them. You should be very comfortable using both. So take a few features and double check with your calipers. Think about which one's more accurate. Sometimes the caliper might give you a little better registration than you can get with micrometer. It's not necessarily always the most accurate in every situation that the micrometer, even though the baseline accuracy is much better, it may not be able to register as easily as a micrometer can. And then we're going to, as we go through, these prints don't have a lot of GD&T call out, but we're going to check for some circularity, cylindricity, and parallelism as we're doing this, which is always a good practice. Even if there's no call out for it, you're going to want to check that it's still reasonable, that whatever circularity, flatness, form error, parallelism, whatever is there is reasonably good for your tolerance. Because if it's large, then you may have an issue with your manufacturing. And let's read the third one real quick. We're going to practice adjusting your pressure and holding the mic in different positions. Use gauge blocks and standards to develop your pressure. So pressure is key, is really key. If you watch the other video where I demonstrated how to use these, how to use a micrometer, I showed you an instance where I could really affect the measurement just on how much pressure I was applying. I was ignoring the ratchet. I was ignoring my personal feel, and I was just cranking down as hard as I could. You can really change a measurement. So when you know something is an inch, let me do, let's do a 150. I know this is 150, so I can practice my feel on how tightly that this should register when I'm close to 150. Okay, so I know, okay, my own well-developed personal sense of feel pretty much got it right away, second nature. But if you wait until you have that, you don't know how much pressure to put, well, just bring it in until it gets to the reading you know it is, and that's your pressure. And then just keep trying to repeat that. Try to repeat it with other gauges, or sorry, with other sizes of Joe block, with other gauges as well. Different micrometers are going to have a different feel. So once again, to follow along, print this out or download it and follow along with me. as well as the prints. So let's take a look at our parts. We'll start off with this step shaft. It's going to be the most commonly used type of feature, an outside diameter that we use an outside micrometer for. So we're going to go through that, and here's the print, and we will see, it never looks good on the second monitor. We're going to start with that 508 diameter on the end, and we're going to work our way from right to left. So I'm going to open this up, and I'll slide this in there. You see I'm holding it kind of with my single finger. You can use your pinky, you can use your ring finger, however it feels comfortable for you. And then I'm using my feel. I'm rocking the part, trying to get the high points. With a small diameter, it's pretty easy to get the high point, to make sure that you are on center with the part and not off to one side like this. So it's a little bit hard to demonstrate, but you want to be on center, whether you're looking at it dead on, like this case, or whether you're looking at it from the side. You want to try and either rock the part or rock the micrometer if the part is stationary inside of a machine, inside of a fixture. So let's take a look at this measurement, and let's try to read it together. So when you take a measurement and you want to move the micrometer off the part, that should be no issue. All you got to do is lock it in place and very gently slide it out, and then you can read a direct micrometer reading of what that part measured, and you don't need to leave it on there, so you can get a nice clear view of it. So just zoom, focus. Let me get rid of the print here. I think it's focused on that. There we go. All right, so I am like pretty much almost dead on 5.517. I can't see any lines like I can, between 3 and 4, between 4 and 5. There's those 3 lines. I cannot see them after the 5, so I haven't gotten any 25 thousandths yet. I've got 0. So I'm starting at 0.5, and then I'm going to actually add, because I'm falling between the 16 and the 17 on my intersect point, I'm going to add 16 thousandths, and I'm going to get the very last digit, which is probably 9/10 or 8/10. I would say 9/10 lines up the best from my point of view. It's a little bit hard to show that on the camera, but as I rotate this through, and if you check the other camera in front of me right now, you'll see I think 9/10 lined up the best. So we're going to call that 0.5169. Okay? And then it's always good practice. Check more than one point. So I'll check, and you know what? We'll write this down. We'll even write this down so that we can remember what we are measuring. So my first measurement is 0.5169 as a diameter. All right. And we will move on, get another reading. I'm going to do it at pretty much the same level. And what are we at now? We're at a different reading. We're at about 0.516, and let's call it 3/10. I think 4/10 I think looks better. So 0.5164. I'm going to write that down off camera. Okay, and we'll go around and we'll do another one. So we're just gonna quickly read these so that we can move on. 0.516. Let's call it 8. And then I'm going to move down. I was doing all of my measurements on right about this level. I'm going to do another one because features this long tend to have taper or some other form of error. Look at that. I'm now at 0.5 0.512, and let's call it 0.8. I'm going to write that down. And so obviously they ran this part very quickly. You can see the lines on it. Now we're at about 0.513. So kind of a big difference. If I bring back all of our measurements I wrote down, 0.513 was my last one. Call that 0. So here's my smallest, and here's my largest. So if we do the difference between them, 0.5169, subtract 0.5128, get 1/10 there, get 6/10 there. Oh, sorry, 4 thousandths. Can't do math. 4 thousandths. That's how much form error there was in that diameter. It varied from the low to the high by 4 thousandths and 1/10. If we take a look at our print, let's take a look at our print tolerance down here. This is a 3-digit feature, right? 3 decimal places. We'll go to our title block. We'll see that title block requires plus or minus 5 thousandths. So I had 4 thousandths of error, and I'm allowed plus or minus 5. So I'm really allowed a 10,000 tolerance zone. And as long as every diameter I measured was within 5 thousandths of the nominal, I'm okay. But are these within 5 thousandths of the nominal? Let's see. 508 is what I got here. And I've got 512 and 516, 517 almost. So this part is out of spec. Every point I measured. So, that happens. You note it. You can note it on your exercise worksheet that it's out of print. You can note that it's a rejection because it is out of spec, and you can just move forward. So I'm going to move on to the next one, and let's we'll maybe speed up a little bit. We'll just keep practicing reading. So we are headed for a 750 call out. It's on both ends of this print. So we're looking for 750. Side. And let's see what we got. All right, so what do we got? What do you guys think we have? I can see 0.7 definitely. I can see 2 lines, and my intersect with the thimble scale is just under 7. So if you take all that information, I've got 0.7 plus 0.025 plus 0.025 for each line. Let's write this down. So I've got 0.700 because I can definitely see that 0.7. And I have 2 lines, so I'm going to add 25 thousandths because a full rotation of a micrometer is 25 thousandths. And then I'm about 6 thousandths. So I'm going to add 0.006. I'm just before the 7. If you can see that, I'm just before that 7 there. Well, if you check the second camera feed, I don't know why the light is not good on the TV monitor, but it looks great on this second camera. Let me try a little bit lower. Well, take my word for it. If you're looking at the main camera, it's just below the 7. And then we're going to grab that last digit. From my point of view, as I rotate it through, it looks like the 9,000th. Maybe the 8, I think the 8,000ths, sorry, the 8/10,000ths lines up. So we're going to add 0.0008. And that's going to be our final reading. So I know I've got 750 plus 6 would be 756 plus 8/10. So I'm at 0.756 and 8/10. That's my reading for that diameter. Let's do another diameter. The next shaft diameter size is 1.0012. So we're going to have to switch micrometers. And previously I already checked it on the standard, so we're good to go. Might want to check it with another intermediate level, but for this exercise we're just going to keep going. And we're going to take a look and grab kind of right in the middle. And wow, look at that. On the nose, 1.012. I don't know if you can see it right there. Dead on. I could check a few more places. Right? It's a little bit off at that place. It's maybe it's just a hair under 13 or a hair over 12. So it's one of the key things when you're measuring a part is that they're not perfectly round. Parts off of a lathe don't come off perfectly round. Parts off of a mill, even less so. So definitely keep checking all the way around, up and down the length, just to be sure you're getting everything, especially with tight tolerance stuff. A lot of people sometimes assume, well, if it came off of a lathe, it's going to be straight, it's going to be round, it's going to be concentric, it's going to be, no run out error, and you just can't assume that. And even the best lathes I've seen, there's built-in error in that mechanical system of the lathe. There's some built-in error in how we're checking it as well. So definitely want to forget that assumption and keep going. Assuming that it's not perfect and you're gonna look for the error. So that's pretty much it that you can do with a step shaft. You can keep doing these diameters and keep recording them here on your check sheets. I'm going to move on to the angle block. There's a few things we can do with a milled part, just like a lathe, a turn part. So we've got our print, which you can find on the website, and pretty much all we can do with an OD mic right now is going to be the overall thickness here, the overall length here, 4 inches. Fortunately, I don't have a 4-inch mic. That's one of the downsides to using micrometers. And there's a 2.340 overall length here. I don't have a mic in that size with me either. So we're just going to handle with that 1 inch, which we did in the other video, in the main video, but we can see what else we can do. So I will be using my 0 to 1, and we're going to open it all the way up to the 1 inch side. And we're going to grab that thickness. Now what do we think this is? I'm looking at the scale. Try not to bump it. And how many lines can we see? We can see 0.9 and we can see 0. So where are we, right? We can see the 0.9 and then we can see the 0. And then over on the thimble scale, we're between 0 and 1. So right away, I know where we are, but I will definitely explain it to you guys. So let's assume we're at 0.9. We're not quite all the way to 1. So how many lines can you see? From 0.9, you're at 0.9 and then 3 lines, and maybe you can see that 4th line of the 0 there, right? Maybe you can, maybe you can't. How you're going to know is if you've reached that line is you're going to look at the thimble scale. Are you past 0? Are you before 0? So we're past 0, which means we've arrived to that fourth line and we're past it. So we're actually already at an inch, and then we're going to add whatever tenth scale lines up. To my naked eye, maybe it looks like 6/10. And let's roll through it. Yeah, I think 6/10 lines up best. So we're at 1 inch and 6/10 at that spot. Okay. And that's because we're just past the line. So I'm going to do another spot. I'm going to do it in this corner now. All right, and I'm going to do that technique where I just lock it and just gently slide it off. Now, what do we think this one is? Okay. And let's focus and get this away. There we go. So what do we think this one is? It's the same thing. I can see 0.9 and I can see the 0. And the thimble scale is lined up between 22 and 23. So are we already at 1 inch and 22 thousandths? Or are we less than 1 inch and we need to add 22 thousandths to the 0.9? Okay, so let's figure that out. So let's assume we're at 0.9, and usually my assumption is I'm at the lower number and then I'm working my way up to it. So we're at 0.9 and I can see 3 lines and I can actually start to see the fourth line. But have I reached that fourth line yet? Well, because I haven't reached 0 yet on this scale, still working my way there, I haven't gotten there yet. So in this case, we're going to do 0.9, we're going to add 3 lines, and then we're going to add 22 thousandths to that. So 0.975 gives you your 3 lines, plus 22 thousandths, 0.997, right? If I did that right, 0.997. And now we need to add the tenths, whatever lined up. So from my naked eye, it's like about 8/10. Let's take a look at the scale. Look at the 7/10 actually looks like it lines up the best. So I don't know if you can see that in the camera. So again, we're going to be at 0.9977. That'll be our final reading. So one of our readings was at 1.000, about 5/10 over an inch, if I remember correctly. This one's below an inch by a few thousandths. So let's verify that with our caliper. We've done this before. My thicker side was over here, right? It's showing me about above an inch or right at an inch, a little pressure. And then I did my second measurement over here on this side. And you can see once I get everything registered, it's a little bit lower. So this can be a great tool to double check your work. This is a little bit easier to check because I can grab so much more area with a caliper than I can with the micrometer. The caliper is also going to allow me to do more range, right? We talked about this in the caliper video, but I'll be able to get a lot more of these distances than I can with the micrometer. So with the micrometers I have, can we measure anything else in this feature and on this print? Because I'm seeing a few actually. So let's keep going. Let's take a look at this corner of the print. See these steps, 0.315, 0.610, 0.840. Well, those are in the range of our micrometer. Now, can we get our micrometer on them? Let's see. So I'm going to unlock this. I'm going to try to get that first one. It was a 315 step. And just like any other tool, you want to look in this corner and you might see some radiuses left over from the machining process, and you won't want to grab onto those. You're going to want to grab onto the flat parts. But I can very easily get, I'm kind of rocking the tool, rocking the part, trying to make sure it seats correctly. You probably heard the ratchet click a couple times, but those were false clicks. I didn't have it perfectly square. So now that I have it perfectly square, there goes my 3 clicks. I slide it off. We know we're supposed to be near 315 if this thing is in print correctly. And you're just about 310 and about 10 thousandths. Let's take a look. Yeah, 310 and 5/10 thousandths. So pretty easy to get this reading. Now I can do it in this orientation, or I can flip the micrometer over and do it in this orientation, and you may need to do that in some situations. The head here or this shoulder here might interfere with the part, and you may need to try and flip it over to get a different registration. But in this case, I'm pretty much clear no matter how I hold it. So this one, without looking at the print, let's see if we can figure out what this is supposed to be. So we're at 0.6 definitely, and I can't see any lines. Okay, so I can't see any lines. I'm at the 5, almost to the 6, so I'm at 0.605 and maybe 7 or 8 tenths. Let's take a look. 7 tenths looks beautiful. So I would say 0.605 and 7 tenths, and our print called for 610. So we're in the ballpark. Not as close as we would like, obviously. Some of this manufacturing happened on the extreme edges of tolerance, but I'm going to check a few more features. Another feature you can do, I mentioned these steps. I can definitely measure this distance the same way. On the print, it's called out the opposite way. It's called out 400 from the top. So I can do a little shot math. If I grab it here first, get a nice reading. I'm twisting. I'm making sure everything's registered flat in 2 kind of pivoting rotations. Slide it off. Let's call that 601 and maybe a tenth. I'm not gonna keep reading the Vernier scale, but I am gonna write that down. 0.601 and a tenth. And then we're gonna measure overall. And let's see what that is. Twist it, make sure it's flat, everything's registered good. I'm gonna walk it off. And I've got 1 inch, 1,000th, and let's call it 3 tenths. Yeah, 1 inch, 1,000th, and 3 tenths. So when I do that subtraction, show that to you. When I subtract these 2 numbers here, 1 inch, 1,000th, and 3 tenths minus 0.6011, I'm going to end up with 2 tenths, 0, 0, and 0.4. So our requirement was 0.4 depth, and using a micrometer, we were able to get that, but not directly. So we were able to use the shot math, use a very accurate measuring device to get, take this distance and subtract this distance to get the pocket depth. So what I'm trying to say is, maybe you want to use a caliper for that method, but you do have the option with a little shot math. Caliper is going to be direct. So let's do a quick comparison with our caliper. This is this is a tricky one. It's a little hard to get that depth bar perfectly straight and lined up. I get 399. So we get pretty close. Good sanity check. I feel like the micrometer registered better, even though it's a direct method with a caliper. It's a little tricky to angle that thing straight. And I feel like the micrometer got really solid registration and very easy math. And I feel more confident in that measurement than I do with the depth bar off the less accurate caliper. So even though the caliper is a direct measurement, there's always that trade-off. So I think that's all I'm gonna show you, but feel free to continue with more of these features. Let's take a look at the rest of our questions here. Flip back. Oops. Always got to fix this when I change monitors. I don't know why. At least you get to see my nice desktop background. All right, so let's look at these questions. So if you can answer these questions by the time you're done with the exercise and you feel confident, then you are going to be very good with a micrometer. So let's see what's important to learn. Here we go. So which style of micrometer do you prefer? Vernier and digital, and why? What are the advantages and disadvantages? So almost everybody I talk to about this question tells me they like the digital because the digital is easier to read. There's no Vernier math involved. And my response to that is that's not a good enough answer for this question. I understand that you want to use what you're comfortable with, and I totally get that. I don't want to use things I'm not comfortable with. But you want to get comfortable with the Vernier scale. It's a necessity if you're going to be in this industry. So maybe a good reason to answer why you like a digital, it is faster. I will give you that. It's faster if you don't have to do the Vernier math. And if you're inspecting with it all day, then definitely it speeds things up. I wouldn't say it's necessarily more accurate. Some people would say that it is because it's digital. And that's also not a good enough reason to say it's more accurate just because it's digital. But if you look at the accuracy comparison from the manufacturer specs, technically they are, they have smaller resolutions and better scales. And the downside is there's more that can go wrong when you have electronic mechanical system working together. So I don't blindly trust them. I like working with the digitals for speed reasons, but I don't blindly trust them just because it's digital. Number 2, so how easy and accurate was it for you to adjust the micrometer calibration? What issues do you see? I didn't need to calibrate anything for this video. You can watch the other video where you saw me kind of chasing my tail. It's a difficult procedure in terms of you can kind of develop a feel over time if you do it a lot. I haven't done it, I don't do it every day. Calibrated micrometer typically every 90 days, and hopefully you don't have to change anything because that means it's been in good condition the whole time. So it's always a challenge. What effect did pressure have on your measurement? Do you prefer touch, ratchet, or friction thimble? That's also something you've got to get a feel for. Practice makes perfect. You're going to have to use it in every situation. So I recommend, in this video series, in this sort of educational environment, it's better to practice and screw up here than it is to do it with real parts and realize you use too much pressure or too little pressure. So I definitely recommend you practice with these, with these known size Joe blocks or pin gauges, so that you can get used to your own feel. What features were challenging for you to measure and why? That's something you want to keep in your mind, that you may, when you go to use a micrometer, is it the best tool? Is there an easier tool? That's something you'll learn over experience. And hopefully throughout this video series, we'll show you some examples of some alternatives. I always bring up the caliper as an alternative because it's such a useful tool, but there are many other styles of micrometer out there, and CMMs and completely different height gauge setups that you could use. So just remember, always be thinking about that. Number 5, again, on the prints, use a highlighter to on the dimensions you would use a micrometer for if you were asked to inspect it in the real world. So this comes down to how well do you understand micrometer accuracy and part tolerance? When can you use a micrometer, and when can't you use a micrometer because it's too tight? When shouldn't you use a micrometer because the tolerance is so big? A caliper is more than accurate. So if you've done the caliper exercise, you go to do this one, think about when would you use the caliper and when would you use the micrometer for this part and for the step shaft. Look at the tolerancing and decide what you would do. If you needed to tool up and write a process plan for this, and you were going to say, all right, we're going to use a caliper for this, we're going to use a micrometer for this. Think about that when you're answering this question. Number 6, what was your experience comparing calipers and OD micrometers? And scroll down. What dimensions could only be done with a caliper instead of an OD micrometer? That's one of the key things to know. You know, when do you trade off between the tools? Even if you're more comfortable with calipers, is the micrometer something you need to just get more comfortable with because it's a better tool? Why were there any tolerances measured that the accuracy of the micrometer might be a problem? So what about large diameter parts? What if those were tight tolerance? So, you know, we only work with what we have. We have this small step shaft here. And so what if this were a much larger part with the same tolerances? Or what if they had tighter tolerances? You know, we're not going to I'm not going to be able to throw every single possibility at you, but I want you thinking about when you see these tolerances, you know, think about, ooh, this is a big diameter. Can I still use a micrometer? You know, there's still some accuracy error with big micrometers. If I have a big diameter and a small tolerance, what do? You know, you can take a look at some other videos specifically where I talk about the inspection, 10-to-1 inspection ratios, uncertainty ratios, tool selection. There's some other videos that will help you decide. But think about that as you're working with your micrometers. And then last one, what GD&T and error could you easily find with just a micrometer? And we went over this in the other video. So if you don't know, just go ahead and flip back to that. But you know, I demonstrated some of it in the video today when I was checking diameters and multiple clockings and axial lengths. This one, and I checked the thickness of the block in a few places. So that is in some ways a GD&T check, even though there's nothing called out on it. It's still important to do as you're checking features. So that's it for me. I hope you enjoyed this video. I hope you were able to learn something about micrometers and how to use them. I want to thank the Laney Machine Technology Department for loaning me these parts, a lot of these tools. It's a great program. I've mentioned it in other videos. They've got they're in the Oakland, Northern California Bay Area, Oakland, and they've got great classes on manual machining, CNC machining, blueprints, inspection. So, excuse me. Sorry if you had to hear that. Thought I'd get through the whole video without losing it, but just barely at the end. So as I was saying, the Laney Machine Technology Department's got a lot of great classes. They offer a lot of certificates for journeymen and apprenticeships and inspectors. So, excuse me. If you're interested in anything like that, please check out the Laney Machine Technology program in Oakland if you're in the Bay Area. So That's it for me. I'm going to go rest my voice before I lose it. And please check out the website, pragmaticmetrology.com, for more of these exercises, more training videos, and hope you learned something. Thank you.